Swayam Prabha. Digital India. Educated India.
Today we will be looking at chemical reactor energy balances. Well, energy balance is something that is so central to chemical reaction engineering, because we have to supply heat or we have to remove heat, and then we must design our systems so that the amount of area that is required for the heat addition or heat removal have to be appropriately correctly done, so that the reaction proceeds as we expect it to proceed. So, this is a very important part of the course in chemical reaction engineering. So, this is something that we get started today, and then see how we can understand what happens. Now, we write our energy balance for a vessel of our interest. I have deliberately taken a vessel of this very crooked shape, just is not to indicate that the balances that we write take into account any shape, in principle any shape, but of course, we construct shapes that are of useful to us, etc. So, we have here a stirred equipment. By stirred, we mean that the intensive properties of the system at different positions in the equipment is the same. So, that temperature, compositions are uniform everywhere, that is the assumption. So, that stirring means that every point inside the equipment has the same intensive property like temperature and composition. We have here F j 0 moles of component J entering, and because of chemical reaction F j moles of component J comes out. Okay. So, F j and F j 0, if they are different, to the extent that they are different, that is the extent to which that particular reaction is taking place. If there is one reaction, for many reactions also we will look at. Now, as per the first law convention, we have taken heat addition into the system as positive, and then heat work that is produced by the system we have taken as positive. Therefore, our statement of conservation says input minus of output plus generation equal to accumulation, something that we have been writing for a long time. Our statement of conservation of mass, we wrote input minus of output plus generation equal to accumulation, and we wrote this about conservation with respect to component J. We always wrote with respect to material balance, we wrote generation of that component J. So, since the rate of chemical reaction is known, we are able to write the rate of generation of component J. Therefore, input output generation, it must be equal to accumulation. Now, when it comes to energy balance, since energy cannot be generated, we say that generation term in the energy balance should not be there. That is why I have removed the generation term. So, input of energy minus of output of energy must be equal to accumulation of energy. So, our energy balance is different from material balance, because of the fact that generation term is not there in the energy balance, but generation term is there in the mole balance, I am not saying material balance, mole balance. Okay. Now, even if you are talking about material balance in terms of kilograms, whatever, the generation of a particular term may be there, because it is getting converted to something else. So, the overall balances there is no change, but individual component balances there will be a change because of chemical reaction. So, what are we saying now? If you are talking about energy balance in a stirred vessel, there is input of energy because of component J is bringing some energy, there is an output of energy because component J is taking away some energy, and then there is input of heat, which is some energy that is coming in, and there is some output of work, which is some energy that is coming out. Therefore, you have input minus the output plus generation equal to accumulation is a statement of conservation of energy. Okay. So, let us now translate all this in terms of some symbols just to understand what might be going on in terms of the symbols. It is easier to work with. So, what is mentioned here is d by dt of E system, SYS refers to the energy inside the system. E is energy, SYS refers to system, E subscript system is the energy of the system. So, left hand side says rate at which energy of the system changes with time. So, that is the accumulation term. As you can see here, the accumulation term here, this is the term that is written. E system is the energy inside the system. S is missing, I will put the S here. Okay. D by dt of E system is the rate of change of energy inside the system. So, that is the left hand side. Now, the right hand side, it is summation I equal to 1 to n E I F I. E I is the energy of component I, and F I is the molar flow of component I. Therefore, E I F I represents the energy that is associated with component I at the input, that means here at the input here. So, summation over all components tells you the total amount of energy that these components are bringing in to the system. Similarly, sigma I equal to 1 to n E I F I out represents the energy that is going out, with all these material. So, E I F I summation means you are looking at the total amount of energy that is associated with all the components that is going out. Notice here we have not taken into account what is called as the heat of mixing, or the enthalpy change for mixing. So, as assumption here is that E I F I, this total energy of E I F I and total energy of E I F I out and E I F I in, there is no what is called as the loss or gain of energy because of mixing. Okay. So, that is the all right. So, that is what is the assumption here. Now, we have plus Q minus W s. So, Q is the amount of heat that you put into the system, and W dot is the amount of work that you take out of the system. So, accumulation equal to input of energy minus output of energy. There is no generation of energy, but there is amount of heat that is put in the input of this another. This is energy that is coming in with the materials. This is the energy that you are putting in through your heat transfer pipes and so on, and W dot is the amount of work that you might be getting into your shaft that might be made to spin, which is turning a motor and so on. So, this is work, this is heat, this is the energy that is coming in because of the fluids that is coming into the system. So, you have here E I as the energy that is associated with component I, which consists of three components. One is the internal energy, kinetic energy and potential energy. So, we take total energy of component I consisting of internal energy, potential energy and kinetic energy. So, E I represents the total energy of the system of the component I, and E I F I therefore represents the total amount of energy that component I brings in, and summed over all species gives you the total amount of energy that is coming in with the species. Similarly, for the output. This one term which all of us may be familiar, but to put it in the context. Suppose we have some material that is going into the system and coming out of the system. I have got here F I P T omega I out minus F I P T omega I in. What is this word? F I P T omega I, if you look at the units of F I P T omega I is specific volume, P T is pressure, F I is moles per. So, this essentially this is a work term, we can understand it here itself. So, let us say it is moles per time, and this is newtons per square meter. This is specific volume, that is cubic meter per mole. Okay. So, cancels off. So, it is meter squared, meter cube. So, this is meter. So, it is Newton meter per second, which is joule. So, this is per second. So, this is joules per second is watt. So, essentially it is energy per unit time, that is what is the. Okay. So, F I P T omega I in is kind of it's coming in, so much of energy is coming in the form of F I P T omega I, and similarly so much of energy is coming in, so much energy going out. So, this difference, what meaning can we attach to this difference? Now, if you look carefully at this, suppose there is a chemical reaction in which F I, this term sigma F I P T omega I and this term sigma F P T omega in and this is out, they are not the same. Okay. Now, here is an instance which says that even in the absence of friction, this term Fi Pt omega I out is different from Fi Pt omega in. Now, if this is greater than this, it means this is positive. If this term is less than this whole term is negative. So, what is that means Wf which we call as flow work, the flow work into and out of a system, that means in this out of a system and into the system, this difference, if it is positive, it means that this particular system, it gives you some flow work. If this is negative, which means that you have to put in work to make this fluid enter the system and come out, even in the absence of friction. So, what we are trying to say is that there can be instances in which you have to put in work, because even in the absence of friction, this term is this minus this is negative. This is something that is to be understood, that you may need to put in work to be able to get system materials in and out of the system, even in the absence of friction. So, this is the point that I am trying to get across to you, that flow work represents the difference between Fi Pt omega I out minus Fi Pt omega I in, and this term in a reacting system can be different. Therefore, this minus this can be positive or negative, and if it is negative, you have to put in work to make fluids go in and come out of the system. So, flow work is an instance where you may need to put in work to get system fluids in and out of the system. Okay. So, what are we saying then? If you are looking at our system here, and we are saying that W dot is the amount of energy in the form of work that comes out of our system, we recognize that this W dot actually consists of two types of work. One is W s, which is shaft work, and one is W f, which is flow work. Now, in an instance where W f is negative, that means you have to put some energy to get fluids in and out of the system, W s is negative, and therefore, the total amount of work, this W s is different from W dot. Okay. That is the point we are trying to put across to you. Okay. So, W s represents the shaft work that we will get out of the system, and therefore, it is that work which is going to appear to us, it is going to turn our turbines, and it is going to turn our motors and so on. That is the amount of energy that you and I will be able to make use of. So, what are we saying now? In our first law, where W dot represents the work that comes out of the system, now can be broken up into two parts. Part 1 is shaft work, and part 2, which is what is called as flow work, which is Fi Pt omega I out minus Fi Pt omega I in. Okay. So, the total amount of work that comes out of our system, which is W dot, we have broken up into two parts. Part 1 is shaft work, shaft 2 is flow work, and we have put the flow work separately. Let us see what advantages we get out of doing this. What I am saying is that this flow work, so let me just sort of go through this once again. W s is the measurable work, since it is available on the shaft. That means, we can actually put in our measuring systems and actually measure W s. Okay. So, that is why it is a measurable quantity, and this W, which is the true work, can be measured only by measuring W f and W s. This can be measured because we know Pt omega I and Fi. Therefore, this is a known quantity, this is an experimentally measured quantity, and therefore, W becomes a quantity that you and I can determine, because W f is a quantity that we know, because Fi Pt omega I for all the components are known, you can sum over all species at inlet and outlet, and W s is the work that we can measure at the motor, because it is turning, and we can measure the work output in various ways. Okay. Therefore, W is a quantity that is measured by measuring separately both W s and W f. All right. Let us try to illustrate this, because some of these things may become clearer if we look at a small example. Let us look at a sulfur dioxide plant reacting with oxygen in air, give you sulfur trioxide. It is a well known reaction. It has been going on in the process industry for last many years. Okay. And it is a catalytic reaction and so on. Generally, air is used for oxidation. Therefore, you get air, oxygen contained in air is used for the reaction and so on. So, I have put some numbers here. I have just taken some data from a factory which processing about 3000 tons per day of sulfur dioxide. So, which is reacting to form sulfur trioxide. So, the numbers look something like this. For the case of this kind of flow, you can calculate all this. I have made some estimates. The flow V naught turns out to be about 250 cubic meters per second, okay. And this flow is measured at some at the reactor conditions, okay. And what is the pressure? Typically, the pressure at which you will pump the fluids is near atmosphere or slightly greater than atmosphere. So, let us say it is 10 to the power of 5 newtons per square meter. So, our situation here is that we have a flow of 250 meters per cube per second and at pressure of 10 to the power of 5 meters per meter squared is coming. So, what is 2 V naught? Fi times omega I is the volumetric flow. So, if sum over all species, it becomes the total volumetric flow. As in essence, this particular term can be seen as volumetric flow multiplied by the molar flow of components. So, this is one way we can understand this. Similarly, you can understand this as flow multiplied by the number of in the sense Fi omega I is flow and then Pt is the pressure. So, pressure multiplied by flow gives you units of energy. So, this difference is what is the flow work. Now, if you put all the numbers, Pt is given, V naught is given. Okay. So, this Pt omega I summation, experience says that about this difference is typically about 0.5% of, that means this minus this turns out to be about 0.5% of what is at the outlet. So, we have written this this as in the form of Pt times V naught multiplied by 0.5%, which is 0.5 by 100 is 0.005. So, what have we tried to do? We have tried to make an estimate of flow work for the case of a 3000 tons per day sulfur dioxide plant, and when you make these estimates for the numbers that we have taken, this turns out to be about 125 kilowatt with a minus sign, showing that this amount of work will have to be put in for the fluids to be put into the system and taken out. In the absence of, even in the absence of friction, you need so much of work to be put in, so that the fluids can go in and come out of the system. Why is this so? It is so because Fi Pt omega I at the inlet and Fi Pt omega I at the outlet are not the same. Okay. And so, that energy will have to be put in appropriately. Okay. So, just to cut the long story short, what we have said here is that flow work is a term which is the energy that is associated with getting material in and out of the system in the absence of friction. And for a plant of 3000 tons per day sulfur dioxide, we have made an estimate that it turns out to be 125 kilowatt with a minus sign, showing that we have to put work into the system. I mean, we have shown at an earlier date that the pressure drop associated with sulfur dioxide, sulfur trioxide, there we estimated that the energy that is required to push the material in and out of the system is something like 2.5 megawatt, taking pressure drops into account. So, taking pressure drops into account, the energy required is 2.5 megawatts. If you do not take pressure drops into account, it is only 125 kilowatt. What are we saying? Pressure drop is a huge activity in the process industry, it requires to be properly managed. Now, why are we saying this? The context of saying this is that when the pressure drops in a process is something we cannot avoid. So, improving catalyst design of course, will reduce pressure drops, understood, but the least pressure drop would be that of flow work. So, flow work is something that is the minimum at which you can work, that means that amount of energy you have to put in anyway, otherwise fluids will not go in and come out of the system. Okay. So, flow work is a measure of the minimum amount of energy that is required to put the materials in and out of the system. So, with this let us look at some examples to understand energy in terms of our interest. I have taken the example of a steam turbine, where what do we have? We have a boiler, to which fluids are coming in and it becomes steam. That steam goes into the turbine and here it expands, and the steam finally condenses and then comes out into the condenser where it condenses. Okay. And then that fluid, that liquid is again pumped back into the process. Okay. So, what is a boiler of, what is a power plant? Power plant is an instance of a process in which steam is generated in a boiler. It is put into a turbine where it turns the wheels of the turbine, and which in turns turns a motor and so on. for a generator. Now, you have so much of energy in the form of heat Q 1 is going into the boiler and so much of energy Q 2 which is thrown into the environment. So, Q 1 minus of Q 2 is really the energy that has been lost by the working fluid, which is in your boiler minus condenser. So, this Q 1 minus of Q 2 must appear as work. So, we have got here W t is the work for the turbine, W p is the work of the in the pump. Therefore, W t minus the W p is what you will be able to produce in this system, giving where you put in Q 1 of heat and then Q 2 of heat output, Q 1 of heat input. So, Q 1 minus of Q 2 under ideal conditions, Q 1 minus of Q 2 equal to W t minus of 4, W t minus of W p, sorry. Is that clear? What are we saying? Q 1 minus of Q 2 is the total of amount of energy that is absorbed by the system, and therefore, that must appear as the shaft work, which is W t minus plus W p. Okay. So, so much of shaft work is done, therefore, that difference must be equal to shaft work. That is what we have said. So, what we are saying here, we are essentially this is also an instance of energy balance, where the energy of steam is used to run a turbine, and therefore, Q 1 minus of Q 2, which is the energy net energy that is absorbed by steam, must appear as turbine work, which is W t and W p. Now, having said all these things, let us now just look at what we are saying in terms of the equations that generate describe the energy balance. So, we have said that F I E I in, F I E I out, this term W dot can be replaced as W s plus W flow work. That is what has been done here. The word W dot has been replaced as W s plus flow work. Okay. That is what has been done. So, essentially the same energy balance we still work with. The left hand side is the state of accumulation of energy in the system. This is the amount of energy that is coming in with the fluids, amount of energy that is going out of the fluids, this is the amount of heat that is transferred into the fluid, and this term minus is the term that is associated with flow work or the work associated with getting material in and out of the system in the absence of friction. So, with this kind of formulation, now we can take this F I P t omega I along with the input terms and output terms and so on. So, that we can combine those and make it, it might look far easier to understand now. So, d by dt of energy of the system now we have is sigma I equal to 1 to n, F I is the molar flow of E I and P t omega I. Okay. You notice here F I E I, this F I P t omega I can be combined. So, that this term now looks like E I, which is the energy, internal energy of the system, and P t omega I is it is an external phenomena because of pressure and so on. So, we have put E I and P t omega I together because of the advantages that it will give us. Okay. So, just like we have done for the inlet term, you can do the same thing for the outlet term, where F I is multiplied by U I by P t omega I. Okay. So, what is it that we are saying? What we are saying is that if you have an energy balance, if you take the flow work into account and then the flow work term appears in the energy balance in this form, you have F I is the molar flow and E I plus P t omega. You can notice here in term here it is a negative, correct, negative net is positive. Therefore, E I plus P t omega I is the energy of the system. Similarly, F I plus energy of this out. So, you have internal energy plus P t omega I is the energy in and that is the energy out. So, since we or shall we say that input energy, output energy, this is the amount of heat that you put in, amount of work that you put in. Therefore, this represents a statement of energy balance after we have made necessary substitutions for our terms. So, our statement of energy balance, as we have said, is d by dt. Now, you can see here on your left hand side the system. On the left hand side also I have replaced the E system by our energy for each component multiplied by the number of moles of component I inside the system. The number of moles of component I inside the system we have taken as N I. See, what I am saying here is that the number of moles here we are assuming that the N I moles of components present here, each of these N I moles has specific energy, so E I, and then E I consists of U I, G I, Z I and then small u I. So, all that is taken into account and that is how our system now looks like this. Okay. So, you have on the left hand side E system, this is E system which consists of Ni multiplied by this is internal energy, this is kinetic energy, this is potential energy, this is the term associated with the flow work, which is now we have brought in appropriately. It goes from I equal to 1 to n number of species, all these I equal to 1 to n, which is number of species. So, notice here that this term, this whole term ui plus uibs, this is the total energy. So, this is something like what is called as internal energy, and this is something like PV term, which is. So, this looks like our conventional nomenclature, what is called enthalpy. Okay. So, you have inputs and you have the outputs plus q minus ws. Notice here this ws, previously we called it as w dot, which we said was equal to ws plus flow work, and that is how we this flow work we put it in terms of Pt omega I and so on, and then rearrange this equation. So, that this equation now looks slightly different from what we started with, and the form in which this equation now looks is something like this. With all the simplifications, what we have is this term, you notice here this term ui plus Pt omega I, it is termed as Hi. That is what we have done here, Hi, and then you have this kinetic energy, this is the potential energy. Okay. Notice here this term is not there. So, notice here that on the left hand side the term Pt omega I does not appear, but on the right hand side it appears. Okay. Is it clear? Because this term flow work is associated with flow, and therefore, in the left hand side is only accumulation, therefore, flow work does not appear, that term does not appear. Therefore, on the left hand side I have subtracted it by putting Pt omega I. So, that this term Hi minus Pt omega I by definition, Hi minus Pt omega I by definition is ui. You see, that is how it is written on the left hand side. Okay. So, this is the statement of energy balance for a system which is well stirred, which means every position inside the equipment has same composition, same temperature, or in other words all intensive properties are the same at different positions of the system. Okay. Now, we can simplify this further, which I have done, so that we have some more advantages, which I will do right now while you are. So, what we have done now is that the left hand side Pt omega I minus okay. So, this term, if this term Pt omega I is not very large, particularly in our reacting systems that we are talking about, this is not a term which is going to be very important. Therefore, it is possible to look at the whole equation in a slightly simpler form by saying the following, that the left hand side, this term and these two terms are not very important, in the sense that the real energy that is associated with our chemical reaction is in Hi, and therefore, this term ui squared by 2 Gzi and Pt omega I are terms which may not be very important. Now, having said this, so of course, this is something that we must verify for our every case we apply these equations, we must convince ourselves that our assumptions are correct, and if it is not, we must come back and use the general form which we have written now, so that we do not make mistakes. So, but in situations of most of our situations of chemical reaction engineering, you will find that these terms can be deleted, these terms can be deleted. So, that the simplified form of the energy balance might look something like this, d by dt of Ni Hi I equal to 1 to n, I equal to 1 to n. So, what is it that our equations look like? Our equations look like that left hand side is Ni Hi summation over all species, the right hand side is Fi Hi summation over all species, and then again out term is Fi Hi summation all species plus q minus Ws. So, what we have done is that we have started with the general statement of conservation of energy, and we made certain simplifications, and then we have written our equations now in terms of enthalpy, which is a term which is well tabulated, etc. And then Ni is the number of moles inside the system, Hi is the number of moles coming in, this term HIFI is the amount of energy that is coming in, and this HIFI out is the amount of energy that is going out, all measured in terms of Hi, enthalpy. Okay. Since enthalpies are well tabulated in this representation form, there are certain advantages, because these can be read out of tables, and therefore, our effort in trying to put the numbers becomes much easier. Okay. So, just to put it in the context, what we have done is that we have set up the general balance equation, and then we have written our equations in a form, so that we can simplify, some of the terms can be deleted and so on, and got the final form, in which we have on the left hand side NiHi summed over all species, the right hand side you have FiHi summed over all species, inflow stream as well as outflow stream, Q and Ws are heat and work that goes into and out of the system. Okay. Now, having said this, so we would like to see how this representation that we have done, how does it sort of explain, or shall we say how it is able to describe what happens in different situations of our interest. So, we will apply our equations to a variety of reacting systems. So, every system that we apply, our equations should hold, correct. So, we want to see how our equations sort of help us to understand what goes on in different systems, etc. So, what have we said? We said that our energy balance equation looks like this. Our energy balance equation is F NiHi summed over all species, FiHi input summed over all species, FiHi output summed over all species, plus Q minus W. Okay. So, let us take the example of a power station. Let us say we have a hydel power station. Okay. Now, how does our equations help us to tell what happens in this hydel power station? So, what is a hydel power station? The hydel power station is an instance where you have a reservoir containing large quantity of water. Okay. Huge, many of our irrigation dams are often used to generate energy, because the water is available at a very high level and it can be made to run through a turbine. Okay. So, you have a reservoir which holds huge quantity of water, and then it is at a level which is much higher than our hydel turbine, which is at a lower level. Therefore, you have a difference of height. There is a difference of height, so many meters, some height difference is there, and therefore, that height difference can be exploited to derive energy from that water. So, what does it do? What is it doing? This water of the reservoir is going through a pipeline into this turbine, and this turns the turbine, and this turbine turns up a generator, and that is how we get electricity and so on. So, I have taken this as position 0 and this is position 2. So, we are writing our material or energy balance between two positions 0 and position 2. How does it look? So, we have said on the left hand side our equations, as you can see here, there is d by dt of NiHi, okay, is equal to F I equal to 1 to n FiHi in, I equal to 1 to n FiHi out, plus Q minus Ws. Now, what is Q, what is Ws? Q is the amount of heat that is put in or amount of heat that is lost. Now, if you assume that this Q is not very significant, or in other words, for the application of our interest, we may assume that this Q is not very high. It is not such a bad assumption as far as hydel power stations are concerned, but the fact is that it is an assumption, and every assumption will have to be appropriately validated, checked, to make sure that our assumptions are consistent with what happens in the field. So, let us form and assume that Q is not very important, that means heat losses are not very important. Therefore, this statement of energy balance says that left hand side accumulation of energy equal to input of energy minus output of energy plus flow energy in the form of Q that is going into the system and energy in the form of W going out of the system. So, you notice here what I have done is I have written the energy FiHi and FiNiHi, these two terms I have written it as a pressure energy P by rho plus Cv times T naught minus of Tr plus U naught squared by 2 Gz naught. That means, the energy that is associated with our reservoir at this point 0, what are the energies it is containing? There is an atmospheric pressure. So, this is P 0 by rho. Okay. And what is this T naught minus of Tr? T naught is the temperature at which this fluid is there, it is taken as T naught, and our reference is at Tr. We always take a reference, whatever that may be. So, Tr, therefore, the energy is associated with this fluid present in the reservoir at temperature T is given by Cv T naught minus of Tr. So, you have so much of energy in the reservoir. Okay. Now, you also have situations where U naught is the velocity of the fluid and Z naught is the potential energy of the fluid. So, in this particular case, if you assume that the energy or velocity of the fluid at the surface of this reservoir is not very high or not very, it is not very important. Therefore, this term u naught squared can be neglected. Why can we neglect this? Because on the top of the reservoir, where you have fluid essentially at rest or maybe moving at small velocities and so on. So, for our purpose we can take it as 0. Okay. Or in other words, u naught is 0. What is G z naught? It is the potential energy at which water is available. G z naught is the amount of potential energy. So, what is it that we have? The right hand side you have pressure energy. Okay. This is a sensible heat energy that is associated with the fluid at temperature T naught. This is kinetic energy, it is potential energy. Okay. You multiply this by F. Okay. F is what is the molar flow of the fluid that is going through the Heidel turbine. So, you have the input, what is the output? Output is pressure at P 2 and then with C V, which is the energy associated with the sensible heat and so on. So, that we written as C V times T 2 minus T r, and this is kinetic energy, this is potential energy. So, what we have done is that we have used this equation, and then based on our understanding of the situation, we have converted this H I in and H I out in terms of C V dt. So, that we can take care of the change in the enthalpy of the fluids. Okay. So, that is taking care of C V T naught minus of T, or this is for the reagents, this is for this one. Okay. Is it all right? So, you have pressure, you have enthalpies, you have kinetic energy, you have potential energy, this minus this. Okay. How does it look? Now, when you look carefully at this Heidel reservoir, what is the pressure at this point? It is atmospheric pressure. Similarly, at point 2, which is emerging into the atmosphere, therefore, pressure at position 0 and position 2 are atmosphere. So, what I have done here? I have put P naught equal to P 2. The second thing I have done here is that the rate of change of the reservoir capacity or reservoir fluid accumulation is not very large. Therefore, we can delete the accumulation term in our energy balance. What you are saying is that we can delete this term because this term is not very large. So, putting these two simplifications, left hand side as 0 and the right hand side we knock out terms which we think is not important. Okay. Therefore, we are left with a slightly simpler form of the energy balance, which says 0, which is on the left hand side, equal to G times Z naught minus Z 2 plus C V T naught minus T. So, we have now said that the energy that is associated with the height or in the with the fluid at a height, now it is able to exchange it and convert it into this term C V T naught minus of T 2 or enthalpy. So, what is it that our Heidel turbine is doing? It is using the energy of potential energy and converting it into energy that you and I can use. So, this is the statement of conservation. So, let us do a small example to illustrate how far we can go. This is an example where what we have done is that W s by F, we have written our energy balance equation. This energy balance equation, in this energy balance equation we have deleted all terms excepting the term corresponding to G z naught and Z 2 and T naught and T 2, all other terms are disappearing, excepting of course, the flow work coming from the flow. So, when we do all this, what is it that we get? We get that F s W s by F is given by this relationship. It is fairly straightforward, because simply by replacing these terms, in terms of terms that we know, we will find that W s by F, which is the energy that is produced divided by the throughput of fluids, is given by gravity plus this term. Okay. So, what we are saying now is that the energy in gravity term, okay, can be converted to energy in fluids in the form of C V, and then that relationship is what is given here. Now, we can do some number of small calculations to understand these numbers. Let us look at one such number. I have taken here T naught is T 2 and F is 4000 kilograms, 4000 tons per second. Okay. Very large, and Z naught minus Z 2 is 5. So, these are the things that are some numbers we assume to get to feel for the size of the plant that you are going to be building. So, I have done here you have 10, what is 10, 50 and 4000. 4000 is the flow, this is the flow, and what is 50? What is 50? This is M, this is G, this is M, okay, M, G, H. So, this is M, sorry, this is M. So, this is G, this is H. So, what we are trying to do is that we have a fluid, a hydral reservoir in which you have fluid available at a height of 50 meters. Now, if it flows through a hydraulic turbine with the G value of 10, what will we get? That is what is the answer that is mentioned here. Then if you multiply all this, you get something like 2 megawatts. What we are saying is that if you have a hydel power station, which is able to supply at a head of 50 meters, that means you are able to lift the water to that height. Okay. G is the gravitational acceleration constant, for 4000 is the flow. Okay. So, MGH, that is a term associated with the shaft work, okay, that turns out to be 2 megawatts. So, what we are trying to say here is that if you have a hydel power station in which water is available at 50 meters height, and then if kg per second, sorry, and if so many kg per second water is flowing, then you will be able to generate 2 megawatt of power. So, this is the point being mentioned here, that if you have a water flow of 4000 kg per second, and then if you have a water flow such that the gravitational acceleration is still 10 meters square per second squared, and then this kg, this 50 refers to the height at which the water is available. So, now what we have done is that we have shown that our energy balance can explain situations that happen in a hydel power station. Okay. So, we go on to see how best we can make use of what we know for running our daily activities. Now, let us say instead of doing hydraulic turbine, we do a steam turbine. What are we doing now? Instead of doing a hydraulic turbine, we are doing a steam turbine. How does it help us, or what difficulties does it bring us into? Let us just quickly understand this. Once again, when we have a steam turbine instead of a hydraulic turbine, we want to apply the energy balance. The basic procedure is identical, there is no change. You have a steam turbine where d by dt of left hand side equal to in minus of out, F I H I in, F I H I out plus Q minus W S. So, this Q and this is W S, and this is in and this is out, this is 0. Okay. Why has we taken the left hand side as 0? Because the accumulation terms are quite small in relation to the flow of energy that is through the system. Therefore, we find taking the left hand side equal to 0 is not a serious compromise on the quality of the descriptions that we can provide. Now, what might happen is that this Q is the amount of energy that we put in. Now, we may be thinking that we are putting 100 units of energy, but what actually goes in is only 30. This could happen to us. How do you overcome this? You overcome this by recognizing that this Q may not be a complete description of what is going on. Therefore, we must know all the heat pathways to understand where the problems are. Okay. So, what this equation explains to you is that how we can interpret that information to understand our system appropriately. Now, having said this, I want you to go through this exercise fully, so that we appreciate what we are saying. Our hydel turbine, water was coming in and going out, and we have water coming at 50 meters. Okay. Now, if you put all our numbers, let us take the example of water is coming in at T2, okay, 4000 kg per second of water is coming in, and let us say Z naught, which is minus Z2 is 50 meters. That means, water is flowing from 50 meter height down. Now, if this term, if T2 minus of T0, if T2 equal to T0, what we are saying is that the temperature here T2 and temperature here, which is T0, if they are the same, then we would produce for this 4000 kg per second of flow 2 megawatt of power. If the flow is 4000, if Z naught minus of Z2 is 50, then we will produce in the shaft, that means your generator, because shaft work is so much, 2 megawatts of work. Now, if it so happens that if T 2 minus of T naught, there is a slight temperature difference of 0.05 degree centigrade. Suppose, which means what? This term is not 0, this term is T naught minus, this is actually T 2 minus T naught 0.05, therefore, T naught minus T 2 is minus 0.05. So, I have just put those things here. That means, our shaft work now, it is not 10 multiplied by 50 multiplied by 4000, but it is subtract, you have to subtract this term. Now, we notice here that this term is something like 290, this whole term turns out to be 290 units. So, that 500 minus of 290 is 210 multiplied by 4000. So, now you are producing 0.81 megawatt instead of 2 megawatt. Now, what we are trying to put across here is that in the energy balance, because we have taken into account the effect of change in the temperature of the fluids, that is going in and coming out, that effect in a hydel turbine as per these calculations says can be very significant. In fact, we would expect, after all, energy in water is a form of mechanical energy. Therefore, we would have thought mechanical energies can be transmitted without any loss of efficiency. Here is an instance where you are transmitting mechanical energy with an efficiency of only 50% or less. This is something that you should bear in mind, and therefore, we have to take into account the fact how do we design our pipelines taking the water into our turbine without allowing it to get heated up even by a very small margin. Okay. This is an important part of design which we should take care. I will stop there. When we come next time, we will take these ideas further. Thank you very much.